Hi everyone, it's nice to be here in Coogee. It's my first time in Australia, and I've seen a lot of good papers from the Sydney group, so it's actually nice to be here in person and talk to everyone. So yeah, fancy titles aside, this work is about doing logical gates on LDPC codes. So this is in collaboration with Ted and Thomas from IBM. And yeah, I think two main ideas that are going to be the main theme for today's talk are ways to do lattice surgery for quantum LDPC codes. And this means that our gate set for doing gates in LDPC codes is Pauli product measurements. So, and that gives you the entire Clifford group. So it's sufficient for doing computation with LDPC codes if you have access to magic states. And the second theme would be code switching using, again, surgery. So these are the two main ideas I'll be talking about. And yeah, this is a quantum error correction conference. So I'm sure we're familiar with error correcting codes. And the key idea here is to encode logical information using non-local degrees of freedom. And this helps you protect against local errors. And quantum error correcting codes are parameterized by these three main numbers, n being the size of your code block. It's the number of physical qubits you use. K is the number of encoded logical qubits. And D is the amount of error correcting power your code has. So that's the weight of the smallest undetectable error in your code. Everyone's favorite code for a while has been the surface code. It performs really well. It's also really simple to execute in hardware. And it has the code parameters that are not that great. So that's why it has a pretty high space overhead. And lately, we've been interested in a broader family of codes, quantum LDPC codes. So this includes like a variety of codes, but the definition is quite simple. The two main parts to this definition. One is that each stabilizer check has at most constant weight, so it involves only a constant number of qubits at most, and every qubit participates in a constant number of stabilizer checks. And these can be represented in many ways. This is a popular notation, which is the Tanograph notation. Here, the X stabilizers are shown in squares above and Z as squares below. And this is just for a CSS code. You can definitely also have mixed checks, but it splits up into a tripartite graph in the case of CSS codes, which makes it pretty simple to work with. And the circles represent qubits. So this is just a regular code, but for LDPC codes, the degrees of each of these nodes and squares in the graph would be bounded by a constant. And a notation that is often used in work in surgery uses a short form, where all of these X checks are kind of bundled together into one set, and the Z checks are also bundled together in another set, and the adjacency or the connectivity is described using check matrices. So here HX describes the X stabilizers of this code, and HZ describes the Z stabilizers. And for LDPC codes, these are both sparse matrices. So that's the notation we'll be working with. At least, my goal is to use cartoons more than this notation in this talk, but hopefully it makes the paper more accessible to know the notation. So yeah, LDPC codes, why are we interested in them? They have far better code parameters. They have far better encoding rates, so you can encode a lot more information using fewer physical qubits, and they also have good distances, as we found in recent years. The challenge that comes with this is that you're no longer restricted to local geometry that can be embedded in some sort of topological notion, and physically what this means is you require long-range connections between qubits. So these are some of the exotic families that were discovered recently, but practically another family that's been popular is the bivariate bicyclic family, which was introduced. It was introduced in a paper by Priadko ages ago, which is the 2-block code paper, but a popular, reference is this Bravi et al. From 2023. And as we can see, that the parameters are clearly a lot better for surface code, because if you have distance 12, 144 qubits or 288 qubits would encode just one logical qubit instead of 12. So this is already encoding something like 12-ish times more information. And counting ancillas, it's still higher. But so it seems like there's been a lot of progress in efficient memories. And the next question, at least in the last few years, was how to do gates on these codes. I think the early papers kind of just glossed over the idea. They had an efficient memory, and they teleported to a surface code to actually do the gates. And even the mediating structure to move information to the surface code was pretty large. In fact, it was larger than the code itself. So here, the gross code would be about 288 qubits, so 144 checks and 144 ancillas. And the system that you used to kind of connect it to a single surface code patch was already like 10 times the size or something, 1,300, right? Yeah. So it's a lot bigger than the code itself. So obviously we wanted to retain all the good benefits of these compact code blocks also for computation. So this was pre-2024, and yeah, the main question now is how can we do gates efficiently? And there's been a lot of work in this area, and I guess I guess the history of LDPC surgery in a very concise way kind of goes like this, and there are a lot more works that that kind of came up, but I don't want to maybe spend all day on this. So I guess surface code surgery work has been going on since the early 2000s. And then in 2016, Matt Hastings had 2 papers on weight reduction, which weren't about gates to begin with at all. They were just about manipulating stabilizer codes to make them low weight, to make them LDPC. And there were a number of ideas there that became useful for also thinking about how you can make a logical low weight instead of a stabilizer. So do a measurement for a logical using a combination of low weight measurements. And that kind of that was a big, I think it inspired some really good work. And there was this phenomenon of, seminal paper by Cohen et al. In 2021, where they solved this problem of doing logical gates or Pauli measurements for LDPC codes, for arbitrary codes assuming no structure. But the size of the ancillary was still quadratic, so that's still surface code overhead. And then in 2024, there were a line of works that progressively made a lot of progress, progressively kind of brought down the overhead and solved different nitty-gritties to this work, to this question: how do we do gates for LDPC codes without blowing up the overhead? And I'm going to focus on 3 papers that came out in, I can't see the highlight, but the 3 papers that were released in October 2024, because they have the biggest overlap, I think, and it would be nice to discuss those ideas. And of course, this is the middle of the story. A lot more work has happened since then in 2025, because now that we've reduced the overhead for one measurement, I guess the next question is, what does the full architecture look like? What if you want to do many different gates in your code? And you might also not want to do one gate at a time. So how do you parallelize these different gates? Or you might not be interested in a D overhead, like you don't want to do D rounds of measurements. So how do we reduce the time overhead? So these were 3 questions that kind of were, there's been a progress in that in 2025. So I'm going to talk about the middle of the story. And I think this is interesting because the ideas are simple, and these things form useful primitives for any new scheme you might be interested in coming up with. This is still very much work in progress and lots of room for improvement. So, so code surgery and the October ideas, which broadly we call auxiliary graph surgery. What's going on here? The idea behind code surgery, so here let's just consider this blue patch. This is some code which has qubits that support a logical, and the operation I'm interested in is just measuring the logical operator that's supported by these qubits. And the idea is, behind surgery in general, is to deform this code by adding extra qubits, extra stabilizers, and somehow measuring the logical in this bigger deformed code. So for a simple way to do this is, if I want to measure, let's say, a Z operator supported on these qubits, I just introduce a new Z stabilizer for every qubit that I want to, that supports the logical. And I could introduce extra vertices as well. The graph needn't be just defined by the logical, but this is what I'm doing here. So these blue squares are Z stabilizers, which are each supported on exactly 1 qubit of the logical. So that's step 1. Now we know that this measures the logical because if these are stabilizers, then product of stabilizers is also in the stabilizer group. So the logical is now in the stabilizer group, and its value can be inferred using these measurements. So that's how we measure a logical, just by adding these stabilizers. But this isn't the full picture because the code needs a lot more adjustments. We have a stabilizer code, so we definitely want these stabilizers to commute with the old stabilizers in the code. That's one challenge. We want to make sure the distance of the code stays preserved because that's the error correcting power of the code. And we also want to stay in the LDPC regime. Like, we want this code to not suddenly be some high weight code. So auxiliary graph surgery kind of designs this structure in a more specific way. So not only are we adding these stabilizers to the code, we want to make sure the new structure is kind of resembles a graph. And when I say resembles a graph, I mean that we associate each new component with a graph, with a graph theoretic idea. So here, every Z stabilizer now forms a new vertex in this graph. And I would be introducing edges which correspond to qubits in this graph. So in homology, you would think of this as going up a dimension. So the boundary of the edges would be the vertices, and that's really the qubits being the boundary to the Z stabilizers for those who think in terms of chain complexes. And this graph would also have cycles whenever edges kind of, when they form cycles. So these cycles are what we associate with X stabilizers. And here we would again be going up one dimension in homology, and this would be the two-dimensional subspace, I guess. So that's what the graph looks like. Now, how do we really design this graph? Where are these edges coming from? And so on would be, I guess, the next discussion here. And one more thing that happens is that the original code stabilizers will be modified. They don't stay the same because we've introduced all of these new stabilizers in qubits, and we want to make sure the whole group of stabilizers is abelian. So we need to make sure that all stabilizers of the code commute with the new checks. So let me first talk about the deformation of this code. So these the qubits shown in the blue box are supporting the Z logical. And the Z logical may overlap with some of the X stabilizers of the code. We know that the Z logical commutes with the X stabilizers, so the overlap has to be even sized. And this overlap needn't just be on 2 qubits. It could be on any even number of qubits, 2, 4, 6, and so on. So this can be described as a hypergraph kind of a relation. And any hypergraph can be broken up into a graph just by pairing up different vertices in these even size sets. So for example, here I have, I'm not showing a hypergraph, I'm really showing just 2 vertices, but it's two qubits, but they correspond to 2 vertices in the graph, and I can kind of find a path through the graph that connects these vertices. So that's a perfect matching on this graph. And whatever edges lie in this path, this perfect matching, would be the extra support gained by the stabilizers in the original code that don't commute. And this ensures that these Z stabilizers and the old code's X stabilizers now have an even-sized overlap, because to begin with, when we didn't have these edges, each new Z stabilizer just had an overlap of size 1. That's odd, so it definitely doesn't commute. But when you begin pairing things up, you find a path that makes sure that you have cancellation that's even. And that's the first thing that we do to modify our code. Which is we pair up and come up with a perfect matching. And I guess that now we have a graph. We definitely have vertices and edges. So I guess I'll describe what the protocol is in space-time. You begin with just the code and a bunch of extra qubits that are initialized in some sort of product state. You want to choose the initial state to be something that helps you have some history in terms of error information. So for a Z logical measurement, we find it useful to begin with the plus state, and we do D rounds of measurement of the new code stabilizers. And by measuring the new stabilizers, we can infer the logical value with sufficient confidence in D rounds. So we've measured our logical. That's the merge step. And then after this, we again split back to the original code. So this is the protocol in space-time. And now I guess the question is, why does this preserve the distance of the code? Of course, any arbitrary graph wouldn't work here. What we need to really make sure is that these new Z stabilizers don't clean any support from the original Z logical. Because every Pauli kind of multiplies to identity, so each of these Z stabilizers could in principle reduce the distance of the code. So what you want to make sure is that these new Z stabilizers, if they clean some distance from the code, you kind of gain distance elsewhere when you multiply with these stabilizers. So for example, I'm considering an arbitrary Z logical that's a different one to the original that overlaps this Z logical I want to measure. And let's consider 3 of these stabilizers that also overlap this brown logical. So each of these stabilizers could reduce the weight by at most 3, right? And we don't want to lose any distance. So we consider next what other qubits these Z stabilizers are connected to. But this would be the additional support you would gain, because because when you multiply with the stabilizer, you clean what the overlap is, and you gain support wherever you don't overlap, right? So as of now, we're losing distance, but we consider the new qubits. And as long as you have sufficient number of edges outgoing from the set of vertices, then you know you've gained more support than you've lost. So this is, so the set here is shown in blue, and these yellow vertices are what we call the boundary of this set of vertices. This boundary can be described in many ways. I guess if you think of this graph G using an incidence matrix, where the incidence matrix is just a matrix where the rows correspond to edges and columns to vertices, then you can find the edges that are the boundary of the set by looking at the product. And as long as the number of edges outgoing from the set is greater than the size of the set, you know that this ratio is more than 1, which means you definitely don't reduce support of the logical by multiplying with these stabilizers. So here, actually, I should also add a minimization because I'm minimizing over all possible vectors V. So all subsets of vertices here. And this needn't be something that we enforce on the full graph. As long as we have sufficient relative expansion, just the size of the set that overlaps with this logical, then that's sufficient. So that also means that your graph isn't constrained all that much if you want to preserve distance. So yeah, this idea was really introduced in the Cross et al. Paper and generalized in later works where the idea was, okay, you don't need expansion in the original code to begin with. As long as you can build this graph above your code which has sufficient expansion, then you can preserve distance. So that's good. Now we've made sure that the new code that we have is not worse than the original code that we began with. And I guess the question next would be, okay, we know that this works, but can we always build a graph like this? Like what is this graph always possible? So that's the next focus of this talk, which is going to just show that, yeah, this is a pretty general construction, and you can always build a graph to measure logical. So what do we need for this graph to satisfy the properties we want? We wanted to preserve distance, so it needs to have expansion, edge expansion, as defined before. We also wanted to stay LDPC, which means all of these new connections shouldn't be with too many components. We don't want very high weight stabilizers or high qubit degrees. So that kind of translates into needing constant vertex degree and short matching. Short matchings would just mean that the original X stabilizers would not deform into too many, would not deform and gain support into too many qubits. We also want the new cycles created in this code which are just automatically created when you add edges. Like any sort of redundancy means that you need to gauge fix it, and you do that by adding X stabilizers. So we want these cycles to also not be too long or to be involved into, like, we don't want one qubit to be involved in too many cycles. So anyway, this is what we call our checklist, which is the graph desiderata theorem. These are all the properties the graph needs to satisfy. So it's really now turned more into a graph design problem to solve this logical measurement problem. And another thing that we want is that this graph G is connected, and that also ensures that we measure the logical we want to measure. So yeah, we know that this graph can always be constructed for any logical. So yeah, the nice thing is this means that any logical and any LDPC code can be measured using this scheme. And yeah, how do we go about constructing this graph? Let's look at desiderata 1, 2, and 3, I guess. So we want constant vertex degree, and we still want the graph to have expansion. These are two competing motives here, because constant vertex degree should mean we don't want too many edges, but expansion means we want a lot more edges. And there are enough, I guess, graph theoretic constructions where you can come up with constant degree expanded graphs with high probability. So we sort of import those ideas and just use that theorem here, which is that any sort of D regular graph, any C regular graph where C is a constant, for sufficiently high C can be an expanded graph with high probability. So you can just paste an expanded graph on the vertices that kind of are created by the Z stabilizers. And then you can apply this minimum weight matching algorithm to find short matchings. So why are we guaranteed that the matchings are short? It's because the X stabilizers that overlap with the Z logical, they're also constant weight. The code was LDPC to begin with. We had to use that information at some point, and we use that here. So if the size of this yellow region is already constant to begin with, that means that you will need at most a constant number of matchings. And the matchings being short is guaranteed. Yeah, so that's guaranteed because why is it guaranteed? I think one is original and the other is, okay, I can't remember right now, but maybe I'll remember as I go along. But either way, you can guarantee two-way sparsity for these matchings. But this is good for proof purposes that you can construct a graph, but it's not really that useful in practice. So when we began constructing graphs for original codes for any LDPC code, what we did was we just began pairing up any vertices that were triggered by any X stabilizer that undecommuted. So if you pair up vertices, we definitely have matched them, and we've ensured stabilizers commute. But to boost the expansion, you can kind of do it many ways. You can just paste a known expander on top of your graph, or what we did was just add random extra edges and check the distance of the code. So this ends up being useful in practice. These are pretty randomized constructions, and as you can tell, they're not optimized. So this is definitely a question that a lot of people are interested in, which is how do we construct this graph in a structured and systematic way, and not just as a random construction that we know exists. But yeah, anyway, this helps us check off these 3 desiderata and kind of guarantee that this graph exists. Now, how do we make sure that the cycle basis stays sparse? There are there's a two-way constraint here. One is that we want every qubit to be in a constant number of cycles, and every cycle to involve a constant number of qubits, right? It's the same as the LDPC definition. The matrix should be sparse both row and column. So here, let's consider the qubit degree of cycles first. So you can have the same edge in multiple cycles. Like over here, this orange edge in the middle is involved in 2 cycles. And let's say I don't want a qubit degree of 2. There is, I guess, a starting point, which is that you can kind of find a cycle basis. You have cycles in your code, and you want to choose a generating set of cycles that's already not too bad to begin with. And that's something we imported from a result by Friedman Hastings, where they have a construction for an algorithm. They have an algorithm to construct a cycle basis where every edge is involved in at most log squared d cycles. So this is our starting point. It's not a constant number of cycles, and we want to bring this down to a constant. So a simple strategy is to just take log squared d copies of this graph. So here, if I have an edge in 2 cycles and I want it to be 1, I just take 2 copies of this graph and I connect it, sort of take a repetition, I take a hypergraph product with a repetition code here. I've taken 2 copies of this graph, and I've added, that means additional qubits and stabilizers. And I now consider my cycle basis to just be sort of chosen from different layers of this thickened graph. So this step is called the thickening step. And here I brought down my edge degree from 2 to 1. And as long as if we take log squared d layers, then we have some guarantees. But I think there were still some issues with just log squared d. So in the end, we ended up choosing log cube d as our thickening height, I guess. And that definitely kind of very liberally ensured that we need only a constant, we only have a constant cycle degree. So I think there's some upcoming work where this multiplicative factor is brought down. But as of 2024, this is where the story stood. So we have a multiplicative overhead increase just by thickening this graph to ensure that your qubit degree isn't too high. And that's by just decongesting it by taking many layers. So we use log cube d layers here. And the second thing we want is that each of these cycles is not too long. So as we can see, this cycle shown at the bottom here involves, I guess, 5 qubits. And we maybe want to bring it down to something bounded by 4. So I've added a green edge here. Every extra edge, if you remember in the graph, corresponds to an extra qubit. So there is an additive cost of physical qubits here. But it's only additive, and it's at most log d or something, I think. So it doesn't really worsen the overhead all that much. And this step is what we call the cellulation step. So adding edges means adding qubits. And by enough manipulation of this graph, we've now made sure that this graph stays LDPC. So all the components are sparsely connected. And this we haven't really assumed any structure in the original code. There's no symmetry, no sort of expansion assumed so far to construct the graph to begin with as far as the original code is concerned. So this scheme works for any arbitrary LDPC code, and the overhead is up to polylogs. It's quasi-linear, so that still was a good place to be in as of last year-ish. So far we've described how to sort of measure one logical in any arbitrary code, but we might be interested in more complicated gates than that. So. I think before that, there's one more thing that I think this construction helps with, which is that when you build this graph, you could have a logical, like this blue thing represents a logical, and you could have a logical contained inside the support of another logical. So let's say your Z logical is Z1, Z2, Z3, and you have another logical operator, Z1, Z2, that also commutes with all your stabilizers, but is not in the stabilizer group. So you don't want to measure like every logical out on those qubits. That's measuring too much, and you've sort of collapsed, you sort of learned more than you wanted. So you want to make sure that any logical that's contained within the support of those logical doesn't end up being measured. And here, because the graph G is connected, that ensures that any subset of vertices that I choose will have edges outgoing from it. which means that any product of subsets of vertices, I don't mean product of all vertices, but just a subset, would still have an edge that's outgoing from that subset, and that means that it would have support on any qubits that correspond to those edges. So we haven't really measured any logical that just is a subset of the logicals of the qubits in the blue patch over there, because it would have some support on this ancillary structure, and you haven't measured the subset of the logical. So this is what we call, we don't need to assume the logical is irreducible, essentially, because irreducible means that it doesn't have a logical inside, and that's because of this additional desiderata, which is that this graph is connected. So that's another, I guess, nice thing that we don't end up learning more than we want. And as any subset of vertices always has support on edge qubits. So that's this subset, pink shown here, has support on those 2 additional pink qubits coming out of it. So are there any questions so far? Okay. So this was from all measuring one logical operator, and really the logical has been very arbitrarily defined. So it could be sort of Z1, Z2, Z3, and you could just build a big giant ancillary to measure it. And all that has really, it kind of, I think the previous ideas I've discussed so far. So you have a question?
Yeah, so my question is, when you do lattice surgery, because any lattice surgery, you never want to do any measurements that anti-commute with any of the logical operators, right?
You mean stabilizer measurements? Yeah, that's right. So stabilizer should commute with the logical, yeah.
And then when you do the stabilizer measurements, you get an output that is randomized sometimes.
Mm-hmm.
Do you just conjugate that stabilizer element with whatever answer you get in the projector to the answer that you get? And then so you have to add different stabilizer elements depending on the output. But no matter what measurement you get, they always compete with the.
Yeah, that's actually right. So when you switch from one code to another, you will have old stabilizers that don't commute with the logical that you want to measure, and the new stabilizers would. So I think the first thing in terms of fault tolerance is you want to repeat measurements so you have sufficient history. And based on those measurements, both based on that history and you can infer an overall frame correction that you might need based on the anti-commuting stabilizer. So based on the final measurement results. So I think, does that answer your question?
Yeah.
Okay. So this was, okay. So I think, yes, this so far has described how to measure a logical, which could be even a Pauli product. And I guess I've really shown everything in the CSS picture. So you introduce a stabilizer of the same type as the logical you want to measure. But in order to measure a mixed logical, like X1, Z2, I think this scheme is not so flexible right now, because what we would do would be locally Clifford deform the code to make the logical fully Z-type and then build a structure on top. So that's where we're at right now. I think there are some old work, like the CKBB paper, for example, built non-CSS ways of connecting any sort of logicals, and we didn't really do that yet. But I think in principle, all sorts of measurements are possible with everything I've discussed so far. But we probably want to still make the scheme a little more easy to implement and easy to understand, and that's where I think the next section is motivated from. So I'm going to talk about joint measurements here. And I've talked, all of this construction was measuring a single operator, but very often what we want to do to execute gates is do Pauli product measurements. So we want to measure, for example, this XX and ZZ operator here, and up to some Pauli corrections, this would execute a C0 gate. So for circuits like this, we want to maybe not have to design a graph for every single logical you want to measure, because if you have n logicals and 4 Paulis, the k logical qubits and 4 Paulis, that's 4 to the k possible Pauli products to measure, and that's a lot of graphs to design. So instead of designing a graph for everything you want to measure, the question we ask next is, if you have 2 different logicals, this is Z1, Z2, and I want to measure their parity, is there a way to construct a bigger graph that measures this logical without learning Z1 and Z2 individually? So it's just a joint measurement without learning individual measurements. And the challenge is that these graphs can look very different. Their logicals can also look very different. So how do you even connect these graphs together? So let's step back a bit and think about how this was done in the old days with topological codes. So there's a more easy way to talk about fusing boundaries of codes, right? For example, these two surface codes, they are isomorphic. They have exactly identical looking boundaries. And what you would do would be measure these new red stabilizers that are created as four-body operators in this boundary to learn the product of Z1, Z2, where Z1, Z2 are like, so Z operators I think here are these blue lines here, blue strings, and the product can be inferred by measuring these four-body operators. So, and if you look at each of these Z operators and its overlap on the X stabilizer, then something that we see is that the intersection of the Z string with the X stabilizers has the same structure as the repetition code. For example, here it's 1, 2 is this triangle blue stabilizer, then the square one is 2, 3, and so on. So if you look at just the X stabilizers restricted to the support of the logical, it has a repetition code-like structure. And the same applies to the other boundary, and then we just directly fuse these two boundaries that look just like the repetition code. So the repetition code's canonical form is just this check matrix here, and we know how to work with a boundary that looks like this, or two boundaries that look like this. Sometimes you could even be looking at two different topological codes. So here I have a rotated surface code and a color code. That's the octagonal color code. And once again, if I look at just the Z logicals, then here the X stabilizers are shown in yellow. So these X stabilizers, again, have repetition code-like structure, X1, X2, X2, X3, within the support of this Z string. And similarly, the color code, I think every plaquette supports an X stabilizer. So both the red and the purple one have a repetition code-like structure. So once again, it's kind of clear by adding extra qubits, you can connect these graphs together. And that's something we've been doing with topological codes for a while. So how do we do this for these graphs that we've built for LDPC codes? So the question now I'm going to ask is, can we kind of change the structure of this graph, at least look at the X stabilizers in this graph in a way that resembles the repetition code. So I want to maybe beginning with something that just looks like a graph here. These are all weight 2 rows to begin with, but they're not in the repetition canonical code form that I'm familiar with. So is there a way to kind of massage the structure to get a repetition code? It is nice that these are graphs, not hypergraphs, because that means the weight of every row is 2. Because every row defines an edge, and an edge is only between 2 qubits. So we are starting with a structure that's easy to work with, but now we want to change its basis to something that looks like a repetition code. And this is pretty much the same thing as changing a stabilizer basis. You change stabilizer basis just by multiplying 2 stabilizers. You still have a stabilizer. It's the same group. So I'm going to now try to change this matrix to something that looks like a repetition code. So this basis change can be described as solving an equation, which is like a transformation on G, like a linear transformation that gives you the repetition code. And we can solve this just by solving an equation, but we want this transformation to be sparse because we don't want to multiply too many stabilizers to create one new stabilizer or one stabilizer involved in too many products. So basically solve this equation, TG equals HC. And I've added a P permutation. It doesn't really matter what qubit is first or second because that's just an arbitrary labeling. So I can permute the columns. That's really not permute the rows. That's the ordering of the checks doesn't matter. So let's begin with an arbitrary graph G here. So that's the matrix, and it's nicer to look at the graph actually as a graph. So I'm just going to do that. So each of these edges here represent a stabilizer. So for example, 1, 2 would mean that's x1, x2, let's say. So I'm looking at a lot of weight 2 stabilizers, and I know that Pauli squared identity. So the product of any of these stabilizers, oh yeah, and I'm looking at a spanning tree. So I throw out any redundancy. This is not something I'm not just looking at a graph with cycles right now. And I combine different edges, which means I'm kind of taking products of stabilizers. So if this went by too fast, what I mean is, let's say I have an edge here, that's edge 1, 2, and then edge 2, 3. So reading this off as a Pauli operator, it would be x1, x2, and x2, x3. So the product of these two operators should give us x1, x3. So that's a new kind of edge I've created by jumping over the node 2. And this is still it still belongs to the same stabilizer group. It's still a product of the same 2 stabilizers, and I'm just kind of creating new stabilizers by taking products. So I'm going to now define a path through this graph, which shows you how to combine these edges to create new edges. And that really was our main algorithm here. We call this the skip tree algorithm. So we take the spanning tree of the graph, and we start with some root node. We can choose this arbitrarily. You can optimize it. And then you sort of start from that, and you look ahead. You skip the immediately adjacent node, and you kind of go to the next node that's visible. You keep skipping until you reach a branching point. So every time you reach, for example, the node 3 here in the old numbering is a branching point. So the thumb rule here is you will never label if the node is labeled, you never label its child until all its children are labeled. So that's kind of like a recursive algorithm that we had. So here, for example, if 3 is labeled, I wouldn't label 4 until I'm done with the full subtree that 4 is a parent of. So I kind of skip ahead to 3's grandchild over here, and I keep skipping, and only when I'm recursing back will I label 4. Now I look at the next child of 2, which is 7. So once again, 7's parent is labeled, so I don't want to label 7 until I've labeled its full subtree. And the thinking here is that you want to leave a way to come back. You want to kind of skip through the whole graph, but still leave some sort of a path to come back. And if I'm too greedy and I begin labeling everything, then I need to take a very long jump back. I don't want the size of the jump back to involve too many edges. So here I keep skipping, so I now skip ahead to, so from 4, I don't want to skip to 7 because its subtree is unlabeled. So I skip ahead to 8. And then I begin labeling its subtree using the same kind of rule here. So you'll notice up till this point, I've only combined 2 edges to create like a new edge. But this is the longest jump I've done so far, which is I've combined 3 edges to create a new edge. And something that we can guarantee using this algorithm is that that's the longest jump you'll ever do. You'll at most combine 3 stabilizers. So this transformation that I'm doing, the linear transformation is 3 sparse, at least as far as number of edges are concerned. And because I do the full circuit, you just keep skipping, and you come back to the root. And every edge has now been involved in a way to the end and then a way back. So every edge is involved in only 2 transformations. So you have at most 3 edges in a combination, and every edge in only 2 combinations. So the full transformation is 3 sparse. And I've skipped ahead, I've formed a new graph here. This is a cyclic graph. This is like a repetition code. But the transformation is pretty sparse, and it's guaranteed to not involve too many edges. And now we can apply this to both the 2 graphs we have here. We apply skip tree to kind of decide an ordering of labels. So I introduce a new repetition code along the border. These are d extra qubits for distance d logical. And the qubit, I decide which qubit of the original, which check of the original code this qubit is connected to using skip tree. And and the cost is only d extra qubits. That's the point of this slide, to say it's not very expensive to connect the graphs. You don't need a lot of connections. But this connection is, any cycle you create would involve at most 3 edges on one side, 3 edges on the other, and then 2 edges just to kind of hop between 2 graphs. So overall, that's that cycle of length 8. So the biggest stabilizer you create in this transformation is weight 8, which is, as far as constants go in theory papers, not too bad. In fact, we find that for codes like the BB code, you can even find a much nicer cyclic ordering just by looking at a Hamiltonian cycle in the graph or like a whole bunch of other techniques. So you end up having really low stabilizer weights, not even 8. But 8 is really the worst with any gnarly expanded code you can kind of give us. That's the maximum, that's the maximum weight. So back to the compact anagraph notation, which I didn't end up using, but let's say I have a Z logical, like a Z left and a Z right, and these are not even from the same code. They needn't be from the same code block or the same code block. The structure is it's agnostic to what logical you're looking at. And you have a left and a right graph. So the way to connect this is to just introduce extra checks, and which are these extra cycles and extra qubits. And they have a repetition code-like structure. But the connections will be given by the outputs to skip tree on both the graphs. So that should give you the linear transformation and the permutation on the qubits. So that was just a nice little primitive that we kind of stumbled upon when we were trying to solve like this problem for something kind of unrelated. We wanted to deform the code to begin doing den twists on it, which we realized is pretty hard for LDPC codes. But this result that kind of came along the way kind of helped us connect 2 codes that they can, you needn't need toric code like structure or something, but you can just connect any LDPC code using this adapter. So it's, we call it a universal adapter because it doesn't assume anything on the code. And as you can see, even in this notation a lot more easily, T is 3 sparse row-wise, and repetition code always has weight 2. So the weight of this middle stabilizer is like 3 plus 3 plus 2, so that's 8. That's another way to see this. And that really was the idea behind universal adapter. And you needn't just use this for surgery. Surgery really is not just Pauli product gates. You can also use it for switching between codes, right? So you can use it for magic state injection. That's been at least the idea on the IBM roadmap, that they want to use a universal adapter to connect a magic state factory. You can use this to switch to a code which has gates that are maybe more interesting structure that you might not want to assume in your memory, but you want some other part of your computer to kind of deal with that gate. So the adapter can be used for just having a full architecture with like multiple codes, not just one code, by kind of changing very easily between these codes. So yeah, that was the idea. I guess it's the same thing going on here, which is if I want to do a T gate, I can switch to a code and then do a T gate and then back. Or I could inject a magic T state also using a joint measurement. So this is just standard state teleportation kind of results. And yeah, I think you could also, that way you can keep good properties of like compact memory and also gates. But yeah, these were all the different ideas we looked at. And I'm happy to take questions.
Okay, thanks, Esha. Very interesting talk. Does anyone want to ask the first question? Ken?
So, yeah, thanks for the nice talk. I just wasn't understanding something about the skip tree discussion. So you were talking about stabilizers coming from these edges, and then in the initial graph there were either vertices or cycles. Is that so? Are you just like breaking up the cycles and then looking at the support on this span tree?
No, I think that's a good question. So in the original graph, the X stabilizers were cycles and the Z stabilizers were vertices, right? So I'm sort of looking at a dual picture right now. So in the original graph, in fact, if we describe this using a Tanner graph notation, then the original graph's stabilizer structure was actually described by G transpose, like it was the dual to the, the Z stabilizers were actually not a graph, they were G transpose, like the transpose of the incidence graph. So in the dual picture, you would switch from qubits to stabilizers and from Z type to X type, and that's why, at least if you want to visualize what this means, these weight 8 cycles are created, I think, when I connect the two graphs together. Yeah, so the X stabilizers would be these red cycles that I created. So that's really, and the transformation tells me what edges in the original graph are combined. So the graph here is between the Z stabilizers and qubits, not between X stabilizers, but I'm looking at a dual picture, and that's why I was talking about X stabilizers there.
Can I ask a question about that as well? So when you do the skip tree on the two graphs, you get like these two cycles basically, and then you want to pair them up. Does it matter like how you identify the base vertex?
You mean the root vertex of the skip tree, or?
Yeah, the root vertex of the two things. It seems like that would be arbitrary. And still
yeah, so far it's random. I think that's another thing to optimize, in fact.
Okay, but you have like these two trees, and then you want to kind of merge the cycles, but you can also rotate them like relative to each other, and then it would still work, or do you have
Yeah, it works up to permutations. So is that answering your question?
I think so, yeah. Good. Does anyone else have that?
So if you rotate it, basically P changes, and then you just get a different T that solves the equation. So the equation that we had was, so if I choose a different node, so the original numbering is pretty arbitrary. Like this numbering doesn't really matter, but that's really the degree of freedom that I'm kind of summarizing as this additional permutation P here. So if I change the numbering, then I would get a different solution for T. Yeah. So yeah, the root node is pretty arbitrary. So I think this algorithm can be optimized in terms of like choosing what is the best spanning tree, then what is the best root of the best spanning tree. But regardless of what you begin with, you can get an answer that's not too bad, I guess, is the conclusion. Sorry, was there a question?
Hey, Jackie, you had a question?
Yeah. So this being a universal adapter, presumably because of its generality, it has more resource overhead than if you were to say make an adapter specifically for some class of codes. So I was wondering the use case for the universal adapter is the hope that like let's say there's some new class of codes, is the hope that we can start probing it right away with like a separate experimental key, let's say, in parallel with the construction of like code specific optimized adapters? Is that like the
Yeah, so in terms of, you mean practical uses. Yeah, I guess to take a step back, the question, I mean, whether we even need an adapter at all, because the adapter actually overall is a little bit bigger than just maybe building a graph for the Pauli product. So you're already using something slightly bigger, but there the use case was that you can sort of, you've already built a chip that measures one single Pauli product, one single operator, and you can connect this a lot more easily. So in terms of chip design, that was a simplification. But now the second question, which is really your question, which is why have this universal scheme instead of like a specialized adapter? So I personally think you should just build a specialized structure to connect two graphs. And in fact, for the BB code, we did find that, and just finding a Hamiltonian cycle and connecting just gave us a repetition code with a nice permutation P. Like we didn't even need the transformation, we just needed a permutation. So I think, I do think that the moment you want to begin getting very picky about designing hardware, you want something specialized always instead of general. But this is a starting point for like, not thinking too much. So. And also maybe if you need to switch things between different codes, like you already have an adapter for like, you already have maybe some connections for skip tree for like one code that you have and you choose a different code, then I think it should be, reusability is always good, is what I've heard as a design practice. But I don't think it's a big pitch to really use adapter, yeah.
More questions? Yeah.
Yeah, so are you able to provide some intuition as to why the log squared thing was not sufficient? Or
Yeah,
like,
yeah.
Why is log, or polylog kind of sufficient at all? Is that just because of the sort of typical length of the cycle?
So let me see if I remember. So you have an edge, so you have a cycle basis. Maybe let's go back to the correct slide. That's a while ago, but if people remember, there was a graph with, so I have an edge that can show up in multiple cycles. That's this orange edge here. And we can begin with a good, so this cycles are generated by some basis. So we can begin with a basis where you have an edge in log squared D cycle. So we definitely, if we want to use the decongestion strategy, we definitely needed log squared D to begin with, because each edge is in log squared D cycles. But each of these cycles is also something like log D long, which could mean that actually you have log squared D times log D cycle collisions. And you don't want any cycles colliding on the same qubit. So this was like a very loose bound, I think, which is that you assume like a log D cycle length, but not all of them would be log D length and so on. So it's not really it's just a bound that we know is true, because the previous one we couldn't really guarantee with log squared. But I think Alex has been looking at something that is log depth, and there may be more people, so, or Dom, so maybe we'll see some future results that are better.
More questions? We have time for a few more questions. Well, there was one I was going to ask, which was you mentioned this like surgery, Dane twist surgery.
Right.
I think that's in your paper, right?
Yeah.
Do you think in the end, I think you worked out some techniques to do it, but in the end, do you think we ever want to do that, or should we just do Pauli measurements with these surgery gadgets?
So I would personally just want to use a C0 gate using Pauli measurements the way we kind of did using the synthesis here. The main thing being that the toric code has huge overhead. It's D squared size, but this still needs like log D, quasi-linear overhead. So the overhead is clearly a lot better. The nice thing about the Dane twist is that if you have some architecture that is good at transversal gates, then you kind of just do, the time overhead is a lot lower, because I think you can do a Dane twist in just like one time step, right? You can parallelize it. So you switch to a toric code, and then you just do like a time optimized Dane twist. So basically, this trade-off is space versus time. Like in a toric code, you can do a C0 gate that's time efficient, but here you need D rounds of syndrome measurements. But if you don't mind space overhead, then you can do that.
So in the Dane twist, do you need like a long cylinder, or can you just do it with a very short cylinder?
So we tried to do it with a short cylinder, and we found that the logical kept getting clean during the circuit itself. So you can deform to something. You can easily switch to a repetition code, right? The toric code is just a bunch of repetition codes, essentially. So we can switch to the code easily, but the moment you begin doing the unitary gates, the C0s would kind of clean off support of the logical. So we couldn't,
So it doesn't work?
It doesn't work, you kind of get zero, you lose all distance. It was not distance preserving, and in the end we just added, we thought, okay, typical CKBB trick, just add one more layer and one more layer, and then it turns out you need D layers and you just need a toric code. That was the conclusion.